All right, so in this one, a runner starts at the sound of a gun from rest, and after the first second, the runner is going 2 meters per second. After another second, the runner is going 4, and then after another second, the runner is going 6. And so the question is, what's the runner's acceleration? So it could look something like this, you know, starting from rest and then getting into 2, then getting into 4. And so, yeah, go ahead and write down what you think the acceleration is, work out what you think it is, and after you do that, you can hit play to continue. So go ahead and pause and then hit play when you're ready. Okay, so we know acceleration is the change in velocity over time, and so, you know, if we wanted to, the final velocity minus initial velocity, final 4, initial 2, or initial or final 2, initial 0, or, you know, 4 to 6. Each second, they're getting faster and faster by 2 meters per second. So that's the acceleration there. All right, so remember, vectors have magnitude and direction, and I want you to go ahead and pause the clip, write down as many vectors that you can remember from the first semester that you can, and when you're ready to check, you can hit play to continue. Okay, so displacement, velocity, acceleration, force. You know, we've had quite a few where we have to, you know, have to have direction. There'll be many more as we continue on. Scalars have magnitude but no direction. So go ahead and pause the clip again, and when list some scalars, and when you're ready to check, you can hit play to continue. All right, mass, time, distance, speed, temperature. You know, any of those that have no direction, only a magnitude, are scalars. All right, so for this one, a person walks 25 meters east and 8 meters south. We want to find out what is their distance, what is their displacement. So remember with this, we want to set up a coordinate axis, north, south, west, and east. And remember with this, you have to be very careful when you draw these out. When we do vector addition, we use the tail to tip method. So the first the person walks 25 meters east, so we can draw that, 25 meters east. Then the person goes 8 meters south. So it's important that we draw that from here to here, right? 8 meters south, and then the resultant vector is from the origin to here. No, it should be a straight line. From the origin to here, right? And then we can get this angle theta and get that. Common misconception is to, you know, want to draw, you know, a vector this way and then to draw a vector like going down, something like that, and then draw a triangle gets kind of crazy. So remember, you know, if the person goes east, they're going to end up here, then they're going to go down here, and then the resultant is here. So go ahead and get the magnitude and then the direction, blank degrees, blank of blank. And when you're ready to check, you can hit play to continue. All right, so 25 meters and then 8 meters down, and Pythagorean theorem, 26.25 meters. And we've got opposite over adjacent, inverse tangent, 17.74 degrees. And then, you know, we've got east and south there. So remember, the second blank is where you start, the first blank is where you go. So 17.74 degrees south of east. Now we could describe it based on this angle, you remember that? Or we can do 90 minus 17.74, and that would be east of south. And either way of describing that angle is fine. The distance is 33 meters, and so, you know, we add up however far they go, and we get that there. All right, so for this one, I'm going to have you set this one all up on your own and draw this out and work this one out. Person walks 18 meters west and 5 meters north, and we want their distance and displacement, magnitude, blank degrees, blank of blank. So go ahead and pause the clip, and when you're ready to check, you can hit play to continue. Okay, so 18 meters west and 5 meters north, we get our resultant, and that's 18.868 meters is the displacement. The distance, we just add that up, 5 plus 18, 23 meters. And opposite over adjacent, inverse tangent, 15.52. And we start on west and go north. So 18.68 meters, 15.52 degrees north of west is the displacement. Okay, so for this one, this is getting into free fall. A ball is dropped from a 14-meter tall building. How much time will it take to hit the ground below? Assume no air resistance. And then also, what is the final velocity when it hits the ground? And so if you remember with this, there's some things that we can write down. Its ball is dropped from there, so V initial is 0. It's starting from rest. It's a 14-meter tall building. So we can have, if we look at the displacement, delta x, it's going to fall 14 meters, so the displacement is negative 14 meters. And we want to find out how much time does it take to hit the ground below. Now we also know acceleration, right, is negative 9.8 meters per second squared. And remember, we use negative g whenever we're doing the free fall equations, the kinematic equations. So yeah, go ahead and get your equation sheet out and see if you can find which one will give you time. And then once you do that, we can go from there. We're looking at the final velocity. So yeah, go ahead and pause the clip and do that. And when you're ready to check, you can hit play to continue. Okay, so final height, initial height, we've got that. We've got our displacement is negative 14. And then 1/2 AT squared, and we divide and then take the square root to get the time. It's going to take 1.7 seconds. All right, so now we want to find out is what is the final velocity when it hits the ground. And so yeah, go ahead and use your equation sheet and see if you can find an equation to help you find the final velocity when it hits the ground. So go ahead and pause the clip and give that a try. And when you're ready to check, you can hit play to continue. Okay. So yeah, with this equation, we can find the final velocity. You have it written as V final squared equals V initial squared plus 2a delta x, which is the same equation, is just rearranged as V initial added to the other side. So yeah, 16.57 meters per second. Now, if you notice, it does not give you a negative here. You have to recognize that the velocity is going downward. And so assign the direction. So the velocity is negative. It's going downward. We could have also used V final equals V initial plus acceleration times time, because now we know time, and we will get the same thing there. All right, so for this one, this is a projectile motion situation, a remote-controlled stunt car. It goes off the edge of a cliff with a speed of 13 meters per second in the x direction. If the cliff is 34 meters high, how far from the base of the cliff will the car hit? So if you think about that, that variable here, how far from the base will it hit, is delta x, and that's what we want to find out. Now, if you remember, in the x direction, the entire time, the x velocity stays the same, right? The whole time. And so if we look at our x problem, because the velocity stays the same, again, with no air resistance, the only equation that works if velocity is delta x over t on your equation sheet, it's already worked out for you. Delta x is v times t. And this is what we want. And we know the velocity is 13 meters per second in the x. The question is, what is the time? Now, if you remember from before, if we had, let's say we had a car that we just dropped straight down, right? We know that if this car drops straight down, the one that I've got in green here, if it goes straight down, it's going to take the same amount of time to fall as the red car goes out. And remember, that was an important part of what Galileo talked about. This car going straight down and this car going straight out, both will hit the ground at the same time. So for a y problem, we know Vy initial is 0 meters per second. It's going 13 meters per second, but again, that's just in the x. In the y, it's not moving. It's just going straight out, and so the initial y velocity is 0. So with this, you can find time, and then once you know time, you can place that into your x problem and say, okay, this is how far from the base it'll hit. Because if we know how much time it's in the air, we know the velocity in the x stays the same. It's just going to go over however far in the x. So go ahead and pause the clip and use your equation sheet there. See if you can figure out the time, and then from there, go ahead and hit play, and then you can check, make sure you're all set. Okay, So yeah, for our time, we get 2.634. The displacement is negative 34 meters. It's 34 meters high. Again, the initial y velocity is 0. We have our acceleration. And yeah, from there, we can get the displacement. 34.24 meters is how far from the base of the cliff this car will land. All right, so for this one, the soccer ball is kicked off a side of a 35-meter cliff, and it hits the ball or hits ground 45 meters from the base of the cliff. We want to find out the initial velocity of the ball. So now that we've practiced the other one, go ahead and give this a try and calculate the initial velocity. And again, be the horizontal velocity here of the ball as it's kicked off the cliff. So yeah, go ahead and pause the clip and give this a try. And when you're ready to check, you can hit play to continue. Okay, so we've got our, x problem here is the velocity stays the same in the x the whole way. And again, because of that, there's no acceleration, and it drops 35 meters, so that's the displacement in the y. We're looking for Vx initial. The initial y velocity is 0 because it's just going out in the x. There's no y velocity starting out. And so we can figure out our time of free fall is 2.67. And then we'll find out, we know how far it went, delta x. We know how much time. And therefore, we can figure out the initial x velocity, which is the x velocity the entire time, 16.84 meters per second.